Okay, so good morning, at least in my time zone, everybody. Thank you so much for joining us today for this joint webinar from the Northern Rockies Fire Science Network and the Northwest Fire Science Consortium. My name is Darcy. I'm the new coordinator for the Northern Rockies. And also here today is Autumn from the Northwest Fire Science Consortium. We're very excited to have you all joining us today. Please do put your questions in the Q&A tab at any point, and Spencer will get to those, or at least as many as he can get to afterwards. Our presenter today is Spencer Vieira, originally from Western Washington and an alumnus of Evergreen State College with a Bachelor of Science in Forest Ecology and Management. Spencer has worked as a silviculturist and forest management consultant in the Puget Sound area. This research today is part of his recently completed graduate work in forest and fire ecology at the University of Montana's College of Forest and Conservation Sciences. He is currently an ORISE Fellow at the Alaska Climate Adaptation Science Center, where he models climate impacts and develops tools for climate adaptation, resource managers, and subsistence communities. And with that, Spencer, I will let you take it away.
Okay, thank you. Yeah, hello, and thanks everyone for coming. Yeah, as you just heard, I'm Spencer Vieira, currently work for Alaska CASC, but this study, which only recently concluded, was investigated while I was finishing my graduate program at University of Montana, working with Professor of Fire Ecology Vieira and research ecologist at the U.S. Forest Service Missoula Fire Sciences Lab, Kim Davis. I was brought onto this project as a research assistant funded through a grant from the North Central Climate Adaptation Science Center, looking at post-fire larch regeneration, specifically in the warmest and driest portions of Western larch's distribution, following some work that Kim had done, noting some climatic thresholds to ponderosa pine and Douglas fir regeneration after fire. But we felt like there was time and interest to also investigate post-fire regeneration in the cooler and wetter portions of Western larch's range. And so we applied for and were thankfully offered funding from the Northwest Climate Adaptation Science Center and the Joint Fire Science Program through each's respective graduate fellowship programs. I'm really grateful for these fellowships. They were able to mentor me in co-productive research, so I could work closely with managers and other stakeholders to conceptualize this study so it would produce results that I hope can be more useful and actionable in management context. And in this case, I and my collaborators worked with managers and research foresters from Washington State Department of Natural Resources, the BLM office in Missoula, and foresters from the Nature Conservancy and the Lolo National Forest. At the end of this talk, I hope I'll have given anybody here working with Western larch forests some useful information to consider when we're balancing these tough tasks that we're all familiar with increasing wildfire activity, changing climate, and the real constraint on having limited resources to work with. I think we all came here well aware that the West in recent decades is experiencing quite an uptick in fire activity compared to what we are used to. Specifically, we are seeing an increase in annual area burned, which means more area burning at all severity classes, including high severity fire, where we often might assume the most detrimental impacts to forest continuity. High severity fire translates to more tree mortality, which leads to concerns regarding the number of surviving trees available as seed sources that would support a forest's ability to regenerate after a fire. As shown here, where it's apparent from the abundance of snags that before this fire there was a dense forest, but after the fire, with no mature surviving trees to reseed the area, only shrub vegetation is successfully established. Now, perhaps another forest many years down the line will establish, but it will take many years, and that may not meet our management goals. Many tree species have coexisted with fire for millennia, exhibiting traits advantaging them to resist fires of varying intensity via thick bark or high self-limbing branches, keeping foliage above the flames. And some trees have developed traits that make them more resilient to wildfire by, even after being killed, facilitating abundant post-fire tree regeneration. This can be achieved by having light seeds that can travel far distances to recolonize an area, or via serotinous cones that insulate seeds as the flames pass through, while simultaneously opening up from the high temperatures, therefore releasing seed on that newly opened ground, making them the trees with the first opportunity to rain seed after a fire, and thus the first to establish a new forest. So in mixed conifer forests of the Western United States, wildfire plays an important role stimulating tree regeneration and opening up the canopy and burning off organic soil layers to expose that bare mineral soil that many conifer trees rely on as an adequate seed bed for germination, allowing seedlings to establish and to grow. Yet, as mentioned before, high severity fire can increasingly limit post-fire seed sources to provide seed availability, specifically by increasing distances to those seed sources. Here from Kemp et al. In a 2016 study in the Northern Rockies, they developed some regression curves for the probability of seedling presence of several species as a function of distance to the nearest live reproductively mature tree of each species. In this left figure, you can see that generally across species, there is a strong negative relationship of probability of seedling presence shown on the y-axis to distance to seed source, shown on the x-axis, especially between 100 and 300 meters. In the figure on the right, the species in the study are split up to show that the strength of this negative relationship varies between species, with ponderosa pine having the sharpest decline. So distance to seed source significantly limits regeneration, and this is species specific. Once seeds are present, post-fire conifer regeneration is then thought to be limited by climate. Climatic tolerance are, of course, also species specific. And in comparison to the wide range of temperatures and precipitation that mature trees are observed to be able to tolerate, seedlings have been found to be much less tolerant to stressful climates, such as climates in areas with consistent years of the hottest and driest or coldest and wettest weather. So areas experiencing more stressful climate, like those that would, in this cartoon, be at the fringes of this yellow seedling oval, are less likely to foster seedlings, even if seed sources are around. Yet cooler than average years can stimulate increased seedling recruitment and survival in a relatively hot and dry area. But with climate change, the occurrence of these cooler than average years are decreasing. Therefore, there are fewer climate suitable years, and so too areas for seedling recruitment. This has been observed by several post-fire regeneration studies in several areas throughout the West, including dry forests of the Colorado Front Range, Northern Rockies, and forests of southern Colorado and New Mexico, even in generally cooler and wetter areas up into the subalpine forests of the greater Yellowstone area. It is clearly established that for many years in the western US, climate change is limiting successful tree regeneration with increases in years of warmer and drier climate. At the scale of an individual seedling and their physiology, warmer and drier conditions increase the likelihood of what we call acute thermal cambial damage, as shown here from Rank et al. In 2022 for ponderosa pine. In this synthesis paper, this group gathered data from studies that expose ponderosa seedlings to varying temperatures, shown on the x-axis, for varying durations of exposure, with shorter exposure periods shown here in blue and longer in red, developing a response curve of the probability of ponderosa pine seedling mortality on the y-axis due to these hot temperatures. Ponderosa pine was found to have the highest mortality rates between 50 and 60 degrees Celsius. But also with studies like Sapes and Sala from 2021 and Simeon et al. From 2019, we have a better understanding as to how seedlings are also susceptible to slower deaths, like from warmer temperatures reducing water availability. Warmer temperatures also cause higher seedling water demands, which they can then struggle to meet, leading to a higher risk of hydraulic failure and simultaneous carbon starvation. This cause of death is visually apparent when you see unseasonal reddening and eventual loss of needles shown in these images on the right. So warmer and drier weather can kill seedlings through acute thermal damage of live tissues and drought-induced hydraulic failure. Many are increasingly interested in determinations of species-specific climatic tolerances of seedlings in order to improve our understanding and decision-making of what to do about continuing climate change in this context. Several studies have investigated this by looking at total regeneration densities over a post-fire regeneration period, which is often 3 to 20 years or more, batched together. Then relating them to average of climate over those years or representative 30-year climate normal, which often buries a lot of the temporal variability going on. The study shown here from Davis et al. In 2019 looked into the climate recruitment relationship at shorter timescales, linking yearly recruitment rates to yearly varying climate, which allowed them to further refine our understanding of the climatic tolerances of, in this case, Douglas fir and ponderosa pine to determine thresholds of annual climate limiting the annual probability of recruitment, revealing both good years and bad years for regeneration. They then used these species-specific climate recruitment models to predict across the climate time series to show the annual variability in climate suitability for Doug fir and ponderosa pine. Regeneration. They found that their identified climate threshold had been increasingly being crossed from 1980 to 2015, showing that during that time period, climate suitable years for both species has been decreasing due to climate change and dry forest across the West. So post-fire regeneration studies at annual resolution we're seeing can really help reveal annual trends in climate suitability. So we're seeing climate change reducing probability of regeneration of fire-resistant thick bark species like Douglas fir and ponderosa pine in that lower elevation dry forest area of western U.S. However, for western larch, also a fire-resistant and thick bark species, yet found in the relatively moist forests at mid-elevations, there's not been much study yet at annual scale on the effect of annually varying climate on western larch recruitment. So for a mid-elevation species like western larch, how has climate change impacted regeneration? And I kind of got to wondering, in these relatively cooler and wetter portions of the forest, could competitive interactions or other factors be more limiting to regeneration before climate? Well, here's a map of western larch's distribution from a species distribution model developed by Rayfel and Jakish from 2010, which I use throughout this presentation in my work. On it, I'm going to overlay some other regionally specific western larch regeneration studies, which have had somewhat mixed results. To start, 2 studies in Glacier National Park from Harvey et al. 2016 and Hecker and Turner 2022. They did not detect a relationship between post-fire drought and density of post-fire western larch regeneration. Other studies, like Urza and Seibold 2017, also in Glacier National Park, and Andrews et al. 2022 in the Blue Mountains of Washington, they estimated tree ages with non-destructive methods, so catching that annual resolution of establishment. But they found western larch seedling establishment was higher with wetter post-fire climatic conditions. Povak et al. 2020 in mountainous areas of north central Washington found higher than average temperature years increased larch recruitment in their subalpine. And then a broader geographic study, yet still limited to Idaho and Montana, from Seed and Goking 2020 found cooler and drier portions of western larch's distribution in that region to be most suitable for recruitment. None of those studies examined post-fire western larch recruitment across its climatic range, possibly explaining some of these contrasting results. As I mentioned before, with the support of funding from 2 fellowships, I was able to expand my sampling to study post-fire regeneration across the whole climatic range of western larch, at least in the US, which, while also investigating relationships at annual timescale, helped me to resolve, I think, some of the varying results from these regionally specific studies that I just mentioned. Western larch is a deciduous conifer of high ecological, cultural, and economic value, found solely in the inland northwestern US and southwestern Canada. It's been observed to be most abundant in areas of relatively moderate moisture availability in mid-elevation forests in association with subalpine fir, Engelmann spruce, lodgepole pine, and even sometimes western red cedar. although it also co-occurs in dry forests in association with ponderosa pine and Douglas fir. It's a deciduous conifer that's highly shade intolerant, requiring disturbance to clear vegetation and expose bare mineral soil for new cohorts to germinate and establish. And it both develops extremely thick bark and exhibits self-limbing branches, making it highly fire resistant. But it also regenerates prolifically after fire with opening of the canopy and exposure of bare mineral soil, and raining its light seeds across that exposed ground, making it notably fire resilient. Some have even hypothesized that the past century of fire suppression and forced cessation of indigenous burning has constrained Western larch's range because of the reduction in Western larch's opportunities for establishment. To understand how Western larch forests have experienced fire in recent decades, we did some preliminary analysis to underlie this study. We found that from 1986 to 2020, there's been 946 fires of 405 hectares or greater in size that have occurred across Western larch's distribution. Looking at this in terms of total annual area burned, shown here as multiple of 1,000 hectares on the y-axis, and with bars colored by fire severity, red being high, yellow moderate, and green low. We can see through the years, shown on the x-axis, a statistically significant increase in annual area burned during that time, represented by this lower black trend line. The proportion of area across severity classes only minimally changes, with a small tendency to more moderate severity fire. And relatedly, the gray dash line above that black line is showing, well, you can see it's pretty flat. It's showing that there was no change in the proportion of what is called core area, meaning the area that is more than 100 meters from an unburned or low or moderate severity burned area, getting at seed availability. So there's been little to no change in the basic estimation of seed availability, but increased total area burned comes with more area burning at each severity class, and that includes more area burning at high severity, of which still could have consequences for Western larch. And so I addressed 3 research questions concerning post-fire Western larch recruitment across its range in the US, starting with what is the relationship between annual climate conditions and the probability of annual recruitment after wildfires? How does annually varying climate compare in importance to other factors known to influence post-fire recruitment, such as seed availability, fire severity, and time since fire? And with climate change, how has the climate suitability for post-fire regeneration changed over recent decades? And to investigate these questions, I amassed a data set on the annual post-fire recruitment of Western larch designed to be representative of factors across its geographic distribution in the United States. We selected sites that burned in wildfires between 2000 and 2015 and spanned the full climatic range of Western larch in the US. Sites were to be located only in patches that burned at moderate or high severity. We limited sites to northerly or southerly aspects to maximize differences in microsite conditions, and to locations within 100 meters of at least one live mature Western larch that could serve as a seed source. Finally, sites were in areas that had no records of post-fire planting or salvage logging. With help from a great team of field technicians, we ended up sampling a total of 57 sites, signified by these black triangles on that map. Our sampling aimed to match the climatic range of our study sites to the climatic range of Western larch's distribution, which you can see looking under the histograms of mean AT and mean water deficit. We did pretty well. And then the 57 sites were distributed among 37 different fires and only in patches of moderate and high severity. Sampling was conducted in the summers of 2021 and 2022 using a variable width 60-meter long belt transect at each site, where we recorded aspect, post-fire Western larch seedling density, and distance to seed source, which was measured at 3 different points along the transect using a laser rangefinder and then averaged. We destructively sampled all Western larch seedlings within the transects with the goal of sampling 30 to 40 Western larch seedlings at each site. And for destructive sampling, soil was excavated around the root collar of each juvenile and a stem segment extending at least 2 centimeters below 10 centimeters below and 10 centimeters above the root shoot boundary was removed. We used dendrochronological methods to obtain the germination year of each seedling, so we could bend seedlings by year at each site to calculate annual recruitment rates. We cut samples into consecutive 2-centimeter segments above and below the root collar and sanded the bottom of each segment using finer grit sandpaper up to 1500 grit. Then we counted the annual growth rings of each seedling under magnification and used the segment with the greatest number of rings to determine the germination year. In total, we sampled and aged 1,651 seedlings, determining the annual recruitment rates for each of the 57 sites, creating age structures of post-fire recruitment after the fire. We then translated recruitment outcomes by year to a binary of successful and failed recruitment years using a threshold of 125 seedlings per hectare per year. This threshold was determined by the 25th percentile of recruitment density of the 681 site and year combinations with regeneration. After building our data set, we could then quantify the relationship between climate and Western larch recruitment after moderate and high severity fire, investigating our first research question. To do this, we used boosted regression trees to build a binomial model with annual probability of post-fire Western larch recruitment as a function of wildfire-related and climate variables as predictors. Wildfire-related predictors were field calculated distance to heat source, satellite-derived fire severity, and time since fire from each recruitment year to account for changes to the growing environment through time after the fire. And climate predictors considered were minimum soil moisture from June to August, mean soil moisture from April to May, mean ambient temperature also April to May, maximum surface temperature June to August, growing degree days above 5 degrees Celsius from January to October, climatic water deficit summed from May to September, and actual evapotranspiration summed from May to September as well. Worth explaining further is climatic water deficit, which is a water balance variable representing droughtiness, showing how much water is missing to meet plant needs. And actual evapotranspiration, or AET, is another water balance variable modeling the actual water usable by plants, essentially representing an area's potential productivity. These climate predictors are modeled at roughly 30-meter resolution from the ECTUO ecohydrology model from Minetto and Silverman, and the TopoFire water balance model from Holden et al. 2016. To investigate our second research question, how does seasonal climate compare to wildfire-related factors? We took the relative influence of each predictor in the final model, determined by its contribution in reducing the model's deviance, and summed up the relative influence of variables within each category, being the fire-related predictors and the climate predictors, and then determined the difference in the total influence of each. And for our third research question, how has the climate suitability changed over recent decades? We hindcasted the model over an annual time series from 1991 to 2021 of the selected climate predictors with static variables, distance to seed source, fire severity held constant at their medians. We did this with time since fires set for years 1 through 10 after the fire, and then averaged the recruitment probability for years 1 through 5 and 6 through 10 to simplify things down a little bit. We then evaluated trends with a generalized linear mixed effects model, and then projected that model over spatial rasters of climate predictors for each year to get an understanding of the spatial variability in recruitment probability through time. So the final model that we wound up with predicted the probability of exceeding the recruitment threshold in any given year with an AUC of 0.86, which basically just means that the model is predicting really well. We also assessed model accuracy at 0.75, showing that proportion of correctly classified instances was high out of the total instances. And we also had really good precision assessed at 0.73, showing that the proportion of true positives out of the predicted positive instances was also very high. So this model is doing a good job having high predictive skill. Unpacking the model to reveal results from investigation of our first question. Time since fire was the most influential variable in forming the probability of recruitment, with a relative influence of 56%. The annual probability of recruitment decreased sharply over 10 years. And in the first 5 years, 87% of Western larch recruitment was observed to have occurred. The strong effect of time since fire, leading to a short regeneration period, is consistent with larch's shade intolerance, with time since fire likely proxy for the burned area developing from an early sterile environment to one with more vegetation, competing with Western larch for light. As well, accumulation is likely increasingly covering up that bare mineral soil seedbed that was generated by the fire and that Western larch relies upon so heavily for germination. Distance to seed source carried 25% of the influence in the model, showing an expected negative relationship to recruitment, even though we constrained sampling to within 100 meters of distance to a seed source. We're still seeing a pretty strong effect. Fire severity carried only 60% of the influence in the model and had a modest positive relationship. With having constrained our sampling to solely moderate and high severity fire, it's notable we still see this positive relationship, albeit marginal. I think if we sampled in low severity sites, I'm certain the strength of this relationship would have really increased, but it still goes to show that increases in fire severity support Western larch regeneration, a relationship that I think is pretty well known to many of us and pretty well established in the literature. And finally, our model selection identified growing season actual evapotranspiration and growing season water deficit as the representative climate predictors, with relative influences of 7 and 6%, respectively. These two climate variables each speak to energy inputs and water availability uniquely, and because of this, have been helpful for several researchers in describing species distributions in the past and currently. The annual probability of recruitment of Western larch displayed a hump-shaped relationship with growing season actual evapotranspiration, increasing as evapotranspiration increased from 150 millimeters to 275 millimeters, likely representing a suitable combination of water and energy that bolsters larch's vigor and competitive edge. But then the recruitment probability subsequently decreases from 275 millimeters to 375, likely representing years where the higher productivity of the ecosystem generally switches to competitively excluding Western larch regeneration. The annual probability of recruitment decreased as growing season water deficit increased from 200 millimeters to 500 millimeters, showing that increases in growing season droughtiness as a condition has a continuous effect of reducing Western larch recruitment probability. Results from the model highlighting the influence of growing season climate were consistent with patterns observed in the overall data set. For example, this figure shows counts of recruitment success on the y-axis, split between north and south aspects, shown on the x-axis. And post-fire Western larch recruitment was significantly higher on sites with northerly compared to southerly aspects, as determined by a Pearson's chi-squared test. And this corresponded to differences in growing season water deficit shown on the y-axis of the second figure, which was significantly lower, therefore less droughty on southerly aspects, as determined by a Mann-Whitney U test. Our results for investigation of our second research question, how does seasonal climate compare to wildfire-related factors, showed that cumulatively, wildfire-related factors, time since fire, distance to seed source, and fire severity accounted for 87% of the relative influence in the model. with annually varying climate predictors, those being, again, growing season AET and water deficit only having 13% of the influence. And so a takeaway here is that currently, for Western larch, wildfire-related factors limit regeneration more than climate. Time-since fire just has a substantially large influence in Western larch regeneration, so climate is just less relevant than the occurrence of and residual effects of moderate and high severity fire, it appears. Looking at the selected climate predictors, again, growing season AET and water deficit and how they change through time in representative warm and dry plots, the gold trend lines, and cool and wet plots, the blue trend lines. You can see in this top figure with years on the x-axis and values of growing season AET on the y-axis, that during the period 1991 to 2021, there's been a significant decrease in AET by about 2.2 millimeters per year. And below this figure, with growing season water deficit on the y-axis, you can see there's been a significant increase in water deficit by about 3.7 millimeters per year. And just for reference, this map shows the portions of larch's distribution we are considering warm and dry in gold, or cool and wet in blue. And we determined this by splitting the distribution at the median value of a 30-year average annual water deficit from 1991 to 2020. Forgetting the trends to instead look at the annual variability in climate averaged across plots, which I forgot to mention that the black thin lines in the background here are showing that annual variability for the individual plots. But the thicker blue and gold lines are those averages across plots. And we can see there is some variability year to year. If we lay a line over the AET figure at that 275 millimeter point, which is the top of that hump of the relationship of AET to recruitment probability, we notice that over time, that 275 millimeter line is being crossed more frequently, at least in those warmer and drier areas, signaling decreasing climate suitability in generally warmer areas in recent years. But overall, the average growing season AET tends to stay above that 275 millimeter line in recent decades, when decreasing AET actually contributes to increasing climate suitability. Shown in a different way, since 1991, the decrease in AET have been increasing probability of recruitment through 2021 in most areas in recent years, while the increase in water deficit since 1991 has been decreasing the probability of recruitment across the distribution through 2021. So the trends in these two climate variables thus far may have had somewhat of a net neutral effect on post-fire Western larch recruitment when we're thinking about the entire range. Yeah, when we're thinking about when we're considering climate suitability across that whole range of Western larch, which is somewhat shown here, getting at research question 3. How has the climate suitability evolved over recent decades? So here we hindcast the model over the time series from 1991 to 2021 of both growing season AET and water deficit, with fire severity and distance to seed source held constant at their medians. And as you can see, climate suitability for the warm and dry areas and the cool and wet areas begin to diverge, especially in recent years. Looking at these as trends over recent decades, we can say that climate suitability for regeneration of Western larch in warmer and drier areas have been decreasing, while cooler and wetter areas have been increasing. Though it's important to say that the rates of these changes have been pretty minimal, with a decrease of 0.01% in these warm areas and an increase of 0.02% per year in these cooler areas, signifying that climate change has thus far had a pretty minimal impact on climate suitability of post-fire Western larch regeneration except for maybe in some very specific areas. This contrast with the trending decrease in recruitment probability from the Davis et al. 2019 paper looking at ponderosa pine Douglas fir. Yeah, there's some contrast. These figures from that paper split recruitment probability for each species across different ecoregions: California, Colorado, Northern Rockies in the green, and then the Southwest. And instead of calculating the averages of the first 5 years, they sum everything together. So to start with, recruitment probability is pretty low for these species in low elevation dry forests where they constrain their sampling. And over time, the climate suitability for recruitment has reduced significantly for both species in most ecoregions from 1980 to 2010. So a little bit of a different story than what we're seeing with Western larch. Back to this study, if we speculate a bit here and go with the expectation that trends in climate persist in the direction they are going, then in the future, it's possible we might start seeing a decrease in climate suitability throughout Western larch's range, or an increased decrease in the warm and dry areas, and that cooler and wetter areas shifting from having increased climate suitability to decreased climate suitability. So as mentioned before, the relationship of recruitment probability and AET is currently hovering above and below that sloping edge of the hump-shaped curve at around 275 millimeters. And if AET continues to decrease, at some point, the decrease will switch from, in some areas, increasing recruitment probability to all areas decreasing it, adding to the continued decrease on recruitment probability from increasing water deficit. So even though in recent decades, climate trends have been fairly stabilizing Western larch recruitment probability, it's possible we might start to see a decrease in overall climate suitability due to the same trends in climate in the future. But within the scope of our study, we can say that the past few decades of changes in climate suitability of Western larch has been minimal. The interannual variability in recruitment probability averages across plots has only varied 8% during this time period, ranging from just 59 to 67%. So things are still looking pretty good. So far, I've shown you hindcasts of recruitment probability for those average time since fire years 1 through 5 across plots, which, like I just said, had only varied from 59 to 67%. But after hindcasting for average time since fire years 6 through 10, we see there is a dramatic drop in recruitment probability, ranging from about 25 to 32%. So the first 5 years after fire is critical for Western larch regeneration, with the early sterile environment and exposed mineral soil seed beds required for larch germination to establish. Looking at this spatially, this is the 30-year mean climate suitability for the period 1991 to 2020, projected across the geographic distribution of Western larch in the US. Post-fire Western larch recruitment was, as you can see, broadly suitable in agreement with the time series I was showing before. In this figure, for time since fire years 1 through 5, the darker the blue, the more suitable area. And to put some sidebars on this, recruitment probability ranged from about 0.51 to 0.78 for the entire Western larch distribution, according to this 30-year average. But in this figure, with recruitment probability for time since fire years 6 through 10, now showing, now the darker the red representing the less suitable area, you can see recruitment probability dramatically diminishes, ranging from 0.19 to 0.39. So across Western larch's distribution, there's broad climatic suitability for regeneration after fire, but there is this big drop in recruitment probability 5 years after the fire. Currently, post-fire management aims to perform interventions to maintain forested areas after fire within the first 5 years, and this really lines up well with this critical window for natural regeneration of Western larch, fortunately. So to summarize this a bit, For our first research question, what is the climate suitability of post-fire larch regeneration? Actual evapotranspiration and water deficit during the growing season best describe climate suitability for regeneration. AET has that hump-shaped curve to recruitment probability representing increasing AET's transition from supporting to inhibiting recruitment, likely from competitive exclusion, from overtopping vegetation growing in. And as water deficit increases, recruitment probability just continues to decrease for Western larch. For our second research question, we found fire-related predictors influenced Western larch post-fire regeneration more so than climate. This is mostly carried out by the outsized influence of time-sense fire, emphasizing larch's need for that early seral environment to germinate and establish. And for our third research question, our results suggest that ongoing climate change had only minimal impact on Western larch's recruitment, but if, at least in recent decades, but if climate trends continue, decreases in AET will likely switch from improving climate suitability in some of those areas to reducing it, compounding the effect of that increasing water deficit, causing the decrease in climate suitability. Also, our results suggest that increases in annual burned area by wildfire in recent decades in Western larch's distribution may have promoted increased Western larch regeneration overall by providing more opportunities for recruitment. In fact, observations of increased Western larch recruitment in recent decades have been observed by some studies like from Hecker and Turner 2022 and Steed and Goking 2020, associated with generation of more early seral stand conditions. These observations led to Hecker and Turner stating that Western larch are well positioned to succeed in the future with more fire, and to Steed and Goking suggesting that increases in fire may offset increases in heat and drought by creating more early seral conditions for larch regeneration. And so continued increases in area burned and moderate severity and high severity fire may increase natural regeneration of Western larch as long as a seed source is nearby, but we shall see. Finally, our study has three important management implications, which can directly inform forest management activities that seek to maintain Western larch as a component of future forests. First, efforts to allow for or generate spatially heterogeneous burning with moderate and high severity patches with the use of managed wildfire or prescribed fire at higher intensities will likely create more opportunities for Western larch recruitment, so long as a high severity patch size retains a seed source nearby. Second, our results clearly support current forest management practices that focus post-fire regeneration assessments and efforts in the first 5 years after wildfire, which we found to be particularly important for Western larch. Further, if planting is necessary due to lack of a seed source, at least in those warmer and drier areas, our findings support focusing planting efforts on northerly as compared to southerly aspects where that water deficit are generally buffered. Finally, our results suggest that ongoing climate change has yet to have considerable impact on Western larch recruitment, giving managers some time to consider management activities for when climate change impacts do emerge, and also acknowledging that they are emerging to some degree in specific areas, I'm certain, within Western larch's distribution, and this model generalizes over that some. So, therefore, in a world where managers increasingly have to prioritize among these multiple objectives related to climate adaptation and maintaining forest resilience, I think Western larch appears to be maybe less immediately vulnerable to climate change impacts than some other conifer species and forest types, such as some of those in the warmest and driest portions of the Western US, which maybe could garner more attention. And with that, yeah, thanks to you all for being here and being interested in Western larch. Thank you, Darcy and Autumn, for arranging this webinar. I really appreciate it. And just one little plug, it's worthwhile probably checking out this Regen Mapper tool found at this URL I have posted up here. This is from Zach Holden at the Missoula Fire Sciences Lab. It's an online tool for post-fire reforestation planning that I think most of Region 1 has adopted at this point. It's pretty easy to use. When fed geospatial data on fire severity in a recently burned area, it'll spit out some predicted probabilities of natural regeneration by species and some suggestions for reforestation. And it works at 30-meter resolution, so at spatial scales that are meaningful for reforestation planning. And my model from Western larch from this study will soon be folded into this tool soon. And yeah, I think we might have time for some questions or discussion. Thank you.
Thank you, Spencer. If you can look in the chat, I believe we have a question posted there. And if anybody else has questions, go ahead and put them in the chat or in the Q&A while Spencer's answering that first one.
Yeah, so I have a series of questions from Justin Cruteau. Will you be suggesting planting Western larch up in Alaska? I don't think quite yet. Although when I've been up there, I've been happy to see some Eastern larch in some of the bogs up there. So larch isn't too far from me. Also, he says, please speak to 1 to 5 or 6 through 10 year success in light of the partial plots shown in research question 1. I think maybe we're talking about that partial dependency plot where we see that big drop in recruitment probability due to time-sense fire. I think that time-sense fire is really representative of the whole ecosystem developing after the fire, and Western larch just gets shaded out. And also another important factor is it really relies on that bare mineral soil being exposed to for those seeds to get in there in order to germinate and establish. And I think as soon as a little bit of duff layer develops after 5 years, it just doesn't have access reaching to reach to that bare mineral soil. And so that's probably why we see that big drop. Third question here is, did you state that AET is representative of competition more than climate? And yeah, I guess there's I should be more nuanced with that. AET, I think, it's a complicated variable representing water balance. It's really associated with precipitation. Higher precipitation generally is higher AET, but this is going to play out differently and be in different areas, and it's going to be related. Basically, what I'm trying to say there is that within the distribution of Western larch, this increase in AET in this Northwest context is likely playing proxy for just higher ecosystem productivity due to that good combination of energy inputs and water inputs that's causing the ecosystem itself to just kind of outcompete Western larch. So Western larch isn't catching an edge, except for when AET is kind of a little bit lower, like under that 275 millimeter pseudo threshold that I threw in there. When Western larch is actually supported by these increases in AET. And yeah, also, yeah, very good to hear this positive outlook. I was pretty happy about it too. And again, this is a model, which means that it generalizes over a lot of the variability that's actually out there. And I'm sure managers will have noted specific situations in their own areas in the recent decades where this isn't playing out exactly as how I spelled out here. And we expect to see climate change affecting Western larch quite a bit in the future, in which case, keep an eye on the work of Justin Croteau, who's got a lot of ideas and work going to help out with that. Let's see, Brad Isbell, can you speak on the viability of seed sources for Western larch? Will seed stay viable after 5 years? I didn't look too much into seed viability of Western larch, and maybe you're speaking to like the seed bank. If seed that's rained on the ground maintains viable on the ground for that period of time, I would say likely no for Western larch, but I don't really know the specifics on that. Hopefully there's more seed raining from the trees that survived the fire that should be still persisting though. So keeping that that input there. It does make me think, for some reason that made me think about larch genetics and some other thoughts on climate adaptation when it comes to Western larch, and thinking about how climate is going to be impacting things and how to adapt to it. And I'd like to also plug Beth Roskilly's work up at University of British Columbia. She either just finished or is working on finishing a PhD, and she's got a lot of common gardens with Western larch where she's looking at supporting the migration of genetics, and seeing if that's a viable route for supporting Western larch in the future.
There is also, Spencer, a question from Kurt over in the Q&A.
Nice.
It seems that seed periodicity would be an important predictor of regeneration post-fire. Did you consider incorporating periodicity into the study?
Seed periodicity. I'm not familiar with that term, but maybe that's getting at mast years, things of that sort, and how that's affecting. And that's something that we didn't look into. It's pretty hard to account for that. Requires being out there year after year at each plot, catching seeds and measuring how much seed inputs there are. I think that is something to consider. Is really important. I would love to include it, and there are studies, I believe, that are looking into that and should be considered alongside this work.
Any other questions or comments or additional resources that people want to add to the chat? I do quickly want to plug. So I dropped in the chat. The Northern Rockies Fire Science Network does have a hot topic for post-fire tree regeneration, which is a curated collection of previous webinars on the topic, science briefs, science reviews, and other resources. So that link is in the chat. And there's also a link for a survey if about today's webinar. If everybody has a chance to fill that out, that is very helpful to us in putting together future webinars. Okay, if there are no further questions, then thank you so much, Spencer, for sharing your work today. And thank you so much, everybody, for attending. We appreciate you taking time out of your day to learn about fire and climate and Western larch regeneration with us.
Yeah, thank you, everyone. I really appreciate you showing up, being interested. Feel free to reach out. I'd love to hear how climate change is affecting Western larch in your neck of the woods. So thanks.